Hello, everybody. Welcome to our monthly Science of All Protein seminar. My name is Amy Huang, and I'm the Associate Director of Scientific Ecosystems at the Good Food Institute. For those of you who are here for the very first time, welcome to our community. The Good Food Institute is a nonprofit think tank 100% driven by philanthropy, and our goal is to build a world where alternative proteins are no longer alternative. And we see all of you as very central to that mission. So if you're looking to take a deeper dive into the science of plant-based fermentation or cultivated meat technologies, do hop over to our website and check out our open access resources at gfi.org/science. Alrighty, without further ado, I will introduce our two speakers for today, Dr. Brentan Alexander and Crystal Bleecher, both of Synonym. So first off, Brentan has a strong entrepreneurial background and has devoted his career to mitigating climate impacts through the commercialization of novel technologies. Prior to joining Synonym, Brentan served in numerous executive roles at New Energy Risk, and earlier in his career, he worked as an engineer, tackling a really wide breadth of projects for Fortune 500 companies. Brentan received his PhD from Stanford in mechanical engineering, where he focused on solid fuel gasification and syngas utilization using solid oxide fuel cell technology. He also holds MS and BS degrees in mechanical engineering from MIT. Now on to Crystal. Crystal is a professionally licensed chemical engineer and subject matter expert in fermentation process and facility design. She has over 18 years of experience tackling the challenges of commercializing novel fermentation processes and has very extensive experience in process optimization, value engineering, and sterile and hygienic design. Crystal began her career as a process engineer working for cellulosic biofuel startups, and her career has been dedicated to developing complex engineering solutions like the one we'll learn about today for the renewable fuel and alternative protein industries. So during today's seminar, you'll learn about Scalar, a new techno-economic analysis tool for fermentation designed to empower alternative protein companies with a better understanding of the unit economics required to launch their bioproducts in the mass market. Companies looking for a techno-economic analysis for fermentation can use Scalar to model their costs of building a commercial scale facility and producing at industrial scale. You'll learn a lot about Scalar and also get a live demo today. So I'll pause there and I'll turn things over to Brentan and Crystal, who will tell us more about this powerful new tool that they've built for the ecosystem. As the two of them are presenting, do feel free to drop any questions that you might have for them in the Q&A section of our Zoom bar today, and we'll be trying our best to get through all of them after the presentation. So with that, Brentan and Crystal, feel free to take it away.
Great, thank you, Amy. Good to be here. Good to see everyone. Appreciate the opportunity from GFI to present to everyone this morning on Scalar. So we're going to cover a few things in the topic this morning. We're going to start with some very brief introductions, since Amy already did such a great job of talking to us. Give a bit of a background on Scalar itself. We'll then dive deeper into the technical and financial assumptions that we use to drive the model outputs, and we'll finish up with a case study and live demo. As we go through this, we encourage everyone to follow along. The Scalar tool is live and available at scalar.bio. So as we get started here, feel free to head on over there if you haven't already signed up to get an account, so you can follow along live as we go through the live demo to better inform any questions you have about how the system works and how we actually calculate the outputs that we have. So very quickly, as already been mentioned, I'm Brentan Alexander, Chief Investment Officer here at Synonym. As mentioned, my background is technical, but earlier in my career, learned the hard way that good technology is totally necessary, but completely insufficient to actually get steel in the ground. So we became very interested in how you actually attract new financing sources to early commercial projects, and did that for a number of years at New Energy Risk. Saw over 1,000 projects across the energy transition space in my time there, spanning the good, the bad, and the ugly, and I'd stress the bad and the ugly. It's hard to develop projects, and we saw many along the pathway there. So that's my background, and now we're doing that in the synbio industry.
Yes, and thank you, Amy, for the great introduction. I am Crystal Bleecher, and I head up the engineering group at Synonym. I joined Synonym last fall, but have been working in the industry for a number of years. As Amy mentioned early in my career, that was as a process engineer for the biofuel industry, primarily in startup operations commissioning roles. But then for the 10 years prior to joining Synonym, I worked on the design side, developing process engineering designs for large capital projects for the bioprocessing industry.
So I always like to start with this slide when we chat about Synonym. $30 trillion. You can quibble with the orders of magnitude here, but we all know that SynBio represents an enormous opportunity in the marketplace. Global output attributed to SynBio or biomanufacturing at large at 30 trillion by 2030. Getting to that number is going to require scaling up a number of strains and building an enormous amount of new capacity. And that's where Synonym focuses as a business. SynBio companies are going to need a large amount of biomanufacturing infrastructure to bring new products to market. And at Synonym, we are focused on helping develop and finance the biomanufacturing infrastructure that's necessary for these products of tomorrow. Now, the pathway from early scale to commercial scale is long, it's complex, it's expensive. It involves millions of dollars for demo runs at CMOs. It involves many millions more for development work and engineering work to even be able to start talking about commercial scale facilities. And those facilities themselves tend to be hundreds, if not many hundreds of millions of dollars to build. So at Synonym, we are focused on tool sets to help make that process more efficient and less capital intensive. So helping companies understand the capacity journey from pilot and demo to commercial, scenario planning along the way, matching with capacity that's available in the marketplace, and helping with the development and financing of bespoke or purpose-built commercial facilities for SynBio companies. Now, one of the key products that we've built along our journey here that many folks may be aware of is called Capacitor. And special thanks to GFI for being a collaborator on the Capacitor project. Capacitor is a database of capacity, 250 plus facilities around the world, providing over 49 million liters of capacity. And this is sort of the first stop to understand what capacity is available at different sizes around the world. Now, what came out of starting to build Capacitor and then continuing to build our business is this question of, are you ready to scale? So being ready to scale means having capacity. Building capacity means being able to attract capital. Attracting capital means being bankable. And being bankable means being underwritten. And so we think about the world at Synonym, or at least I think about the world from the CIO standpoint, from this bankability and underwritten standpoint, because when many people in the industry talk about scaling up, they think about it primarily from the technical lens, scaling up strains, scaling up processes. But scaling up also means being bankable and being able to attract the capital necessary to actually scale up. And so being underwritten to know that you're bankable means you understand your costs. What are your operating costs for labor, utilities, SG&A, et cetera? What's the capital cost for actually building a facility? It means understanding resilience of your processes. How do the costs change, and how does that impact profitability of a particular process? What are the primary risk drivers that could impact the profitability of a company? And finally, it means validating returns for potential investors. What scale is necessary to actually reach profitability? What pricing levels for selling is necessary to actually create bankable returns? And so it's through this process of trying to answer these questions for many of our clients that we developed Scalar. So Scalar is a next generation techno-economic model, that's a mouthful, that gives you the critical insights that you need to understand the bankability to get your bioproduct to market. So the focus is on over 50 adjustable parameters. They span technical and commercial inputs. They include things like the size of the facility, information on your product, types of feedstock and yields, what downstream processing is in use at the facility you would look to be utilizing. And from that information, we produce over 10 critical KPIs specific to the bioprocess. So to give you some quick examples, if you looked at a Scalar report, these screens should look familiar to you. Scalar will help calculate and predict things like the capital cost of the facility. So for the inputs provided, if you wanted to build a facility to support the type of process that is outlined, what would that facility cost, both to build and also to run? What would be the cost of actually operating that facility over time? What would the cost of goods be on a per kilogram basis? And then we help with scenario planning. What are the key parameters that actually drive that profitability? What is the impact on product title in terms of profitability on a project, to understand what are the key knobs and barriers to actually reach commercial scale production in a bankable fashion. Now, I just jumped through a lot, going straight from A to B, and the focus of this presentation is really to demystify how do we actually get from A to B? How do we take those technical and commercial inputs and calculate those various numbers? So I'm going to start here from 30,000 feet, give you sort of a broad overview of how we think about the model construction, and then we'll dive into each of these in more detail. So very broadly, starting at 30,000 feet, we take technical inputs. We use those to derive a priced equipment list for the type of equipment that would be necessary based on those inputs. And we use those to calculate a total facility cost. Next, we take those same technical inputs and we calculate operating parameters. How much electricity is going to be used, how much natural gas would be used, those types of things, to calculate what the operating cost facility would be, and how much production a facility would be actually able to support. Using those capital cost calculations, we then determine what is the financing need to actually build something with that cost. And that leads us to actually directly calculating the financing costs for a facility. What does it cost to have debt and equity on a facility of this size and type? We take the operating and production numbers that we calculate. So the production levels we use to directly calculate revenue at a facility. You can then subtract out the operating costs for a facility. And what you're left with is cash left over to pay investors in that facility. And so that's the last step of the model, is then comparing the cash available for investors with the financing costs for a facility to determine bankability. If there's enough cash available to cover financing costs, that's a bankable project. If there's not enough cash available to cover what would be the financing cost for a facility, that project is unbankable. And so we'll get into the details of this now, and I'll turn it over to Crystal to really talk through the critical pieces of the technical model of the Scalar platform.
All right, thank you, Brentan. As Brentan mentioned, I'll be walking through how we take those technical inputs and generating the capital cost for the facility. It's worth noting that the CapEx that's developed in Scalar is reflective of a greenfield facility. So that includes not only the processing equipment, but also the building, infrastructure, and utility systems. So we start with process engineering fundamentals. We start by defining the process flow and developing a mass and energy balance. For aseptic aerobic fermentation, many of the upstream and utility unit operations are the same for a wide range of products being produced. It starts with bulk chemical and feedstock receiving. There's media makeup, media and feedstock sterilization. Then there's the seed and production fermenters, along with the fermentation air compressors and exhaust systems. Generally, there's a harvest tank that provides the surge volume between the upstream, which is a batch process, and the downstream, which can be a continuous or semi-continuous process. That downstream process is a big box right now, highlighted in green, but we'll dive into that shortly. And each process will also include some packaging, as well as the supporting utility systems, such as waste collection and inactivation, water recycle, plant and instrument air, CIP, which is clean in place, steam, and cooling and chilled water systems. So what can vary greatly depending on the type of product that is being produced is the unit operations in the downstream process. So the Scalar tool will ask different questions depending on the type of fermentation that's selected. So whether you select biomass or precision fermentation, and also depending on the type of product that's selected. We do that in order to identify what the process flow is, and therefore what the unit operations are in the downstream process. So currently in Scalar, the precision protein and the dried biomass downstream process flows are well defined in great detail in the Scalar engine. And that's this kind of block flow that I'm showing on the screen now. We do make some high level assumptions for other products, such as lipids and small molecules. But just taking, for example, precision protein, if that precision protein is extracellular, then the very first unit operation is cell separation. However, if the product is intracellular, then we have to start with a pre-lysis cell separation step to concentrate the biomass prior to the lysine step. From that cell separation step, the biomass is sent to a biomass inactivation system. You'll notice that there are questions in Scalar regarding biomass valorization, and that defines what that unit operation is. And the liquid stream is then further clarified in the clarification step. You'll see in this block flow diagram for the clarification step, you have the option of selecting a filter press or microfiltration. But with any of these downstream processing steps in Scalar, you also have the option of selecting none if that step isn't required in your downstream process. Finally, there's a concentration step and an optional secondary concentration step. And if selecting ultrafiltration or any of the TFF, you have the option to specify diafiltration as well prior to a drying step. And so as you can see, there's lots of different configurations for the downstream process, and even within the different steps, there are different equipment operations to be selected. And based off of the selection, Scalar will ask different questions in order to set the process requirements for that equipment. So once the process flow has been defined, and specifically the downstream unit operations, the technical inputs around each unit operation is used to develop a mass and energy balance. That mass and energy balance tracks the total flow throughout the process. It tracks the product flow. It tracks water flow throughout the process. And it also estimates major heating and cooling requirements. So for instance, for aerobic fermentation, the fermenters are highly exothermic. So there's a large cooling requirement in fermentation. For the dryer, there'll be a large heating requirement for the dryer. What I'm showing on the screen here, all of these numbers are just illustrative, and these flow rates and energy requirements can vary greatly depending on the technical inputs that are provided in Scalar. So in the third step, we size the unit operations that were identified in the process flow using using equipment sizing calculations as well as the mass and energy balance requirements. We then compare that sized equipment list against our internal database of equipment cost. That internal database has been developed by obtaining budgetary quotes from vendors for all the major equipment. We've attained those over the last 12 months. And then we use a cost scaling equation to develop a priced equipment list. So the cost of a piece of equipment is equal to the quoted cost of the equipment times the ratio of the equipment capacity to the quoted equipment capacity to the nth power. That n can vary. It does vary depending on the equipment type, but on average, it's about 6/10. And so sometimes that's referred to as the 6/10 rule in cost estimating. Next, we utilize that sized equipment list to develop footprint requirements for different areas within the facility. And then we use a dollar per square foot estimate for each building area. So the different areas of the buildings have different finish requirements, different HVAC requirements, and so therefore the cost of construction is different. We developed those dollar per square foot estimates from analyzing recent project data. And so in Scalar, selecting things like food grade versus industrial grade will have a big impact on what those dollar per square foot requirements are for certain processing areas. From that, we can determine the total construction cost of the building. And I just want to point out again, like all of the examples I'm providing, this table here on square footage is completely illustrative, and the size of the facility will vary greatly depending on the technical inputs that are provided within Scalar. And so this is our fifth and final step of how we come up with the CapEx for the total installed cost of the facility. After we develop the equipment price, which I have shown here highlighted in red, and we develop the building cost, we then use factors to develop the construction bulks and indirects. So construction bulks would be things like piping and civil instrumentation, electrical. Indirect costs are engineering and procurement. There's construction indirects such as equipment rental and scaffolding. There's also startup commissioning cost, tax and freight. One thing I want to point out is that the CapEx that's reported in Scalar does not include project contingency or cost associated with project guarantees. Brentan will touch on this later on when he talks about the financial cost, but there are additional costs to consider, such as contingency when calculating the full project cost. So in this section, I'm also going to walk through how we take those technical inputs and then develop the operating costs. Now, we don't have time to do a deep dive on how we develop all of the operating costs, but I did want to highlight in this table the major technical inputs that influence the different operating costs. In the Scalar report, you'll see one of the first outputs is the direct cost of production on a $1 per kilogram of product produced basis. And that direct cost is made up of variable COGS, COGS being the cost of goods sold, and fixed COGS. Variable COGS are primarily made up of raw materials and utilities. So stepping through these one by one, the first one, feedstock. Often feedstock, the feedstock cost can account for like 30% of the direct costs. And the major inputs for determining that is the product yield on feedstock as well as the feedstock pricing. In Scalar, we also ask about media, base for pH adjustment, inducer requirements in order to estimate bulk chemical costs. And if you go to the Advanced tab on Scalar, which we'll show you in the live demo, you can also specify consumable and SG&A costs. But otherwise, the default for these is a percentage of the raw material cost, depending on the type of fermentation process that's been selected. Next is utilities, and I'm actually going to do a deeper dive on the utilities in the next couple of slides. So moving on to fixed COGS. The fixed COGS are comprised of labor, which I will also do a deep dive on in a future slide, as well as maintenance, tax, and insurance, which is a percentage of the total installed cost of the facility, which we just talked about in the previous section. Moving on to how we come up with electrical costs. There's a lot that goes into this, but from a high level, aerobic fermentation processes use a lot of electricity, and the main drivers for that is the mass and heat transfer within the fermentation itself. For high OUR fermentations, this can sometimes account for 70% of the total facility electrical usage. So starting with a mass transfer, we have two knobs that we can turn for mass transfer. There's agitation as well as the air rate, flow rate to the sparger. Often we refer to that in units of VVM, so standard volume of air per volume of broth per minute. In the Scalar engine, we use the peak and average OUR inputs along with KLA, KLA meaning the mass transfer coefficient. So we take the peak and average OUR inputs along with the KLA equations to estimate the power and velocity requirements in order to determine the agitator and fermenter compressor sizing and therefore the electrical usage. The peak OUR is used to determine the equipment size, and then the average OUR is used to estimate a time average electrical usage for the OpEx calculation. high OUR fermentations are also highly exothermic. We estimate the heat removal as the metabolic heat plus the heat of agitation minus evaporative cooling. So in Scalar, we use a Cooney correlation, which is 0.11 kilocalories of millimoles of oxygen uptake to estimate the metabolic heat. And once the cooling requirements are defined, then we can size the chiller systems and estimate the electrical usage for the chiller compressors. Fermentation temperature is also important because in most locations, the chillers aren't required to operate 100% of the year. In the wintertime, when the cooling tower temperatures are cool enough to maintain fermentation temperatures in the fermenter, the facility can take advantage of what's called free cooling and not run the chiller systems. So in Scalar, we use that fermentation temperature to estimate the percentage of the year that free cooling is available. So a lot goes into the electrical calculation. That's just on the fermentation side, but that is a big portion of the electrical usage for aerobic fermentation facilities. Moving on to water and wastewater assumptions, a water balance is developed as part of the mass and energy balance. Water users include fermentation water and DSP water, but also include water for cleaning, so CIP water, boiler feed water, as well as cooling tower makeup. Often people don't realize that the cooling tower can be one of the biggest water consumers in an aerobic fermentation facility. So want to make sure that that's also included in the water balance. Wastewater treatment requirements can vary greatly depending on the site. So it's important to note that we do not include wastewater pre-treatment equipment in the CapEx calculation. That in Scalar is treated as an OpEx, not a CapEx. So the only wastewater equipment that's included in the CapEx in Scalar is a wastewater collection. So essentially an equalization tank where you could do some pH or temperature adjustments. The default wastewater treatment pricing in Scalar does include BOD, COD reduction, as well as effluent discharge pricing that's consistent with the US Midwest. We will show you when we do the walkthrough, but if you go to the advanced tab of Scalar, you can input the number of operators and lab personnel and daytime staff for the facility. However, if you choose to use the Scalar default, that is a labor model that has been developed based off of the facility size and number of fermentation trains. So the larger the facility, the more equipment, the larger the staff requirement. This org chart and number of staff is just illustrative. It will vary depending on the technical inputs that are provided. And lastly, I just wanted to highlight that the inputs that are used to calculate the production rate. So when we report that direct cost in Scalar, it's on a dollar per kilogram of product produced basis. This is the equation that we use to calculate how much product is produced. So the annual production rate is the titer multiplied by the number of batches, and that's developed based off of the fermentation time, multiplied by the working volume in the fermenter, multiplied by the DSP recovery percentage. That DSP recovery percentage is calculated based off of the DSP unit operations and the process parameters provided for those DSP unit operations. Multiplied by the plant uptime. That percentage as a default is 90% in Scalar, but you can adjust that on the advanced tab. Multiplied by the percentage of successful batches. In Scalar, the default for that is 98%, so that assumes there's 2 in 100 failed batches when operating at steady state. And then all of that is divided by the percent product purity on a wet basis. So how much of your target molecule is in your final product. And COGS will vary significantly based off of those technical inputs. But for precision fermentation processes, variable COGS can account for about 45% of the total cost of production. Fixed COGS can account for about 15% of the total cost of production. And capital service, which we haven't discussed yet, but Brentan will be covering in the next section, can account for about 40% of the total cost of production. In this example, the first column that I'm showing here has a fermentation time of 120 hours and a plant utilization of 90%. In the second column, the fermentation time is 144 hours and the plant utilization is 75%. So that production rate is decreased by 28%. And as a result, you'll see that the total cost of production on a kg basis increases about 29%. If you take a look at the variable COGS on a kg basis, that's about the same. In this case, they're both about $12 per kg. But because the fixed and capital service cost, the absolute costs do not decrease with the lower production, those become a higher percentage of the total cost of production when the production rate is decreased. So with that, I will turn it back over to Brentan so he can talk through how we layer on the financing cost and investor returns.
So using all the technical parameters that Crystal just mentioned, we then layer on the financing model. And the financing costs must be included in COGS. That's me getting on a soapbox. But no factory is free, and this is often a mistake we see some early companies make, is focusing primarily on unit costs related to just pure OpEx. But the cost of actually building a factory and then amortizing that factory over time have to be included in the actual cost of production for our product itself. And so at Scalar, we calculate the cost of actually financing in a couple different pathways: on balance sheet, off balance sheet with third-party equity and debt, which is essentially project finance, and some co-location scenarios are also included in some runs for folks who are looking for 1,000 cubic meters or less, where by co-locating with other producers, some of the OSBLs, some of the utilities like wastewater or electrical loads can be shared. In the Scalar output, the output is heavily focused on off-balance sheet financing, and I'll talk about that decision in the next couple slides here. So to give an understanding of on versus off balance sheet financing, for most companies that we interact with at Synonym, on balance sheet financing means using venture capital dollars. The problem with that is returns of infrastructure assets tend to be not well aligned with the return expectations of venture capitalists. And so venture capitalists look for money at the actual technology level, which means dilution. And they would be making that bet on the belief that project one would be enabling further projects and further scale, because the project itself, the returns from the project just would not be matched to a venture-like return. Off-balance sheet financing, by comparison, project finance is designed to separate the credit quality of a durable asset from the credit quality of the sponsor. The idea is someone investing in the project is investing in the P&L of the project itself, divorced from any upsides or downsides associated with the technology provider. This allows access to lower risk investors who accept lower returns because they're attracted by the contracted revenues and the lower risk of an asset. So essentially, these guys give up potential upside in exchange for downside protection. And the reason you do that is showing this plot on the right here, at least for early stage companies where corporate equity is expensive. The total weighted cost of capital for a project finance transaction where you can bring in some debt and asset level equity is significantly less than the total weighted cost of capital of doing venture capital type investment at the top co. That's not necessarily true for large companies. Large companies have access to public markets, and public credit markets can finance things on balance sheet for low cost of capital. But that's not true for many and most companies in this space. So it's important to understand that off-balance sheet financing requires mitigating those downside risks. This is a bit of an aside, but it's important to understand many companies start their lives as startups, and they're trained to speak about large TAMs and large market opportunities and all the upside that a company has in front of it. Off-balance sheet financiers don't really care about your upside. They much more care about how they're going to be protected from downside scenarios. Venture capitalists are comfortable having zeros in their portfolio. Infrastructure investors get fired if they get a zero in their portfolio. And so they're much more interested in understanding how their downside risk is protected from the structure of a particular transaction. I bring this up primarily because Scalar, the financial model, is meant to calculate on an economic basis whether a project would be bankable based on its economic returns. But it doesn't do any analysis of whether the other pieces of the project are properly downside mitigated to actually enable an off-balance sheet financer to be interested. And so things like, is the EPC contract properly formatted and have the proper controls in it to protect against construction risks, things of that nature. Is the technology validated enough to be viable at scale? Are the commercial bona fides sufficient to demonstrate the market for the product? Scalar does not review any of these items, but they are critically important in understanding whether off-balance sheet financing is actually available for a project. So aside, getting back to the actual model here, how do we calculate leverage that's available to a project in our model? How much debt could be utilized to build a facility? We do that by looking at what's called CFAD's cash flow available for debt service and the loan life coverage ratio, the LLCR. And so try to demystify that a little bit. For a lender that'd be looking to provide debt to construction for a facility, they want to make sure that they're going to get repaid. And they look at two key parameters. One is what is your revenue minus your operating costs? That's how much cash flow is then available to pay debt service. That's known as CFADs. And then they want to know what is the ratio of that CFADs to the debt payment. And that's what's called the coverage ratio. And so in our model, we assume that a lender would be looking for a 2x coverage ratio. So for every dollar of free cash, they would be willing to have essentially a debt payment of 50 cents to make sure there's plenty of buffer and overhead there, so that if prices went up for labor or you couldn't sell the product for quite as much as you think, there's enough buffer to make sure the debt still gets paid. And we price that debt based on a 10-year loan at 10% interest. So based on those parameters, the revenue calculated and the operating costs calculated from Crystal's portion of the model, we can then calculate what is the amount of debt that is available to be put onto a facility. We only allow up to 65% leverage, which is above 65% is really only available to very established asset classes. And if the calculation shows that debt would be under 20%, at that point, the financing costs of trying to get that debt and the fees associated with it just wouldn't justify it. And so we mark that down to zero. And so debt is provided for the project between 20 to 65 if the calculation shows that there's sufficient revenues to support debt. And then the balance is used as equity in the project model itself. The next thing that we do is we then calculate the full project cost. And this is another area that's often confusing for folks who haven't done project development before. Crystal spoke at length a couple minutes ago about calculating the total project cost. That total installed cost is the cost for all the equipment, all the installation, all the labor to install it, painting, all that kind of stuff. But it's actually not the total cost to build the project. There's a number of what's called soft costs associated with financing. And so those are things like project contingencies, working capital accounts to make sure there's enough cash available to pay for staff during the commissioning and startup periods. For debt providers, they generally will require a debt service reserve account. So that's an account with money in it just in case the project runs into some trouble that can cover any debt service payments during a trouble period. And then there's things like transaction fees. And so in Scalar, we account for all of these soft costs when calculating the total cost of an actual facility. And so on the right here is a sample output, illustrative output from Scalar that shows, for a model that calculated a $319 million facility cost, the total all in would actually be something closer to 400 million when you account for all the soft costs, the contingencies, the working capital accounts that are required to actually get a project financed. And so the equity and debt that's raised for a project is raised against this total amount as opposed to just the facility cost amount as required generally by investors. And so we take all this information to then determine bankability. And so revenue is calculated based on the technical inputs that Crystal talked about, multiplied times a commercial input, which is the sales price of the product. We then subtract out the fixed costs and the variable costs, which Crystal's technical model develops. We then calculate the size of debt based on the calculations I just discussed to determine what debt service would be for a particular project. That gets subtracted out. And then finally, we calculate what an equity distribution would need to be to attract equity into a project. Now, for Scalar, we assume that an equity return would be an equity return requirement would be 18%, a targeted leveraged IRR for a 20-year asset life. That 18% is really targeting risk-tolerant private equity investors who would do a project on balance or off balance sheet of this type. This is a parameter that can be changed in the model depending on what your financing source is. For something like venture capital, that target IRR is probably something like 30% plus. But based on a target IRR, we can calculate what would the equity distribution need to be to return enough capital to your investor to justify the investment. And so when you add up fixed cost, variable cost, debt service, and equity, and you subtract that from revenue, what you're left with is pure profit. And if that pure profit number is positive, that means the project is theoretically bankable. It's generating enough cash flows to cover all of its operating costs and all of its capital needs. If that profit turns out to be calculated as 0 or negative, that means the project is likely not bankable, and the Scalar results will show that information to help identify where improvements can be made to try to drive a project towards bankability. So that's the technical and financial model. As we move over now to the case study and actually the live demo, sharing some of the feedback that we have heard to date from many of our users, things like having flexibility in selecting DSP processes, supporting smaller scale facilities, other types of fermentation like gas fermentation. I saw in the Q&A there's a question about continuous fermentation, which we partially support today. Calculating LCA in terms of if we know how much natural gas and electricity are used in various jurisdictions, can we calculate the greenhouse gas impact of that? These are many of the things that are under consideration now for the Scalar roadmap. And so as we go through the case study, encourage folks to put into the Q&A or into the chat any areas where they think improvements could be made or new features could be added that would make Scalar even more useful. So that we can take that feedback to our product planning side to make sure they're included in our future roadmaps.
All right. I think that includes the presentation. What we'll do now is just walk through a case study using the tool. I encourage anyone to that's available to follow along. The first time that you go to use Scalar, you will come up to this abbreviated form. To get started, this is kind of like a Mad Libs. You fill in what type of fermentation process you have. You can name your protein, or you can name your product. We can select protein, lipid, or small molecule. In this case, you want to know if it's intracellular or extracellular. You can select a manufacturing location, input your product price on a $1 per kg basis, what the expected titer would be, fermentation time for batch fermentation processes, and then also select the size of the fermenter and what the total facility size would be. And then the last input for the short survey is if it's industrial or food grade. And then you can select get my results. For the calculation, it generally takes about 30 seconds to run. And the first report that is generated is going to give you some pretty big ranges in terms of annual production, the cost of the facility, and the operating cost for the facility. And that's because we've only filled in a handful of those 50 plus technical inputs. While Oh yeah, here we go. So you can see it's a pretty wide range for all of the results. One thing that you can do to then tighten that range is to answer more questions by selecting this button here. It will prioritize the questions that have the most impact on the calculations. So it prioritizes those first. But if you would like, you can skip that question, or if you're like me and you just want to see all the inputs, you can select View All Questions, and that will take you to what we internally call the long survey, which is just a list of all of the questions. I do want to make sure we have lots of time for Q&A, so I did pre-fill out an example, which I'll swap over to next. But please read through the instructions. It provides a good overview, and it is important that you answer some of the questions in order. So for example, selecting a biomass fermentation, you now see I have a different number of questions to answer in the downstream process than if I had precision fermentation. So the earlier questions can determine what the later questions are. So it's best to step through them in the order of the tabs. I'll just quickly kind of go through each section and highlight a few of the major ones that we talked about during the presentation. So for the product information, obviously we're asking the fermentation type. In this case, I just put in a generic name. What type of product are you producing? Ask some questions about the host organism, the location of the facility, the target sales price for the product, and whether or not, in this case, that the cell biomass will be sold as a byproduct. Moving on to the next section is the determining the facility size and timeline. One thing I didn't mention is that when we determine the capital cost of the facility, we also escalate it to the project year. So that capital cost is reflective of the project year. Then moving on into the fermentation parameters. So we do have a continuous and fill draw selection. We make some high-level assumptions to estimate the throughput with that, but just selecting batch and fed batch for now. Here you put in what that fermentation time is. Even if one thing I want to point out, even if the default number looks good to you, definitely overwrite it and type it in, because that way Scalar recognizes that this is an input, and therefore it will that range, it takes it into account when defining what the range that's provided as the output. The next question is about whether or not it's aseptic. So do the fermenters need to be pressure vessels? Is steam sterilization required? Here is the OUR inputs that I talked about earlier. These become a major input into sizing the chiller systems and air compressor systems. So I'll put in some numbers, some inputs here. And then again, so just an example, if I was to select a fed batch and induction here, you'll see that I now have some more questions to answer down here in the feedstock and yield. So the questions that you answer up front will generate different questions in the further down sections. Going into feedstock and yield, this is where we ask about the product titer, and then also how much cell mass is produced in the fermentation, the feedstock, the price of that feedstock on a dry basis, and then also the yield, so the yield of product, so grams of product produced per gram of feedstock consumed. Here you can go through and select, put in your specific media recipe. If there's components here that you use in your fermentation, you can select other and then just provide a pricing for that. But there's just a default media recipe that's used in the background if you care to skip it. And then moving on into downstream processing, this is where, again, you can select if it's intracellular or extracellular, which determines the DSP process flow, whether or not the DSP requires chilling. Will determine if you have DSP chillers in your equipment list. That product purity, which is a major input to to calculating how much product is produced. In this case, we said extracellular, so we start with cell separation. Again, if we would have selected intracellular, then the first step here would be the pre-lysis cell separation. And then for all of the DSP unit operations, based off of what we select, we have different questions to help determine the mass and energy balance around that unit operation and the sizing for that unit operation. So if I was to select filter press, I would get a different set of questions than if I select a microfiltration system. And then a couple of things that I did want to point out in the advanced tab. Here is where this is that 90% plant uptime that's used in the product rate calculation. Again, it defaults 90%. You can override that. There's this utility pricing in here, which is reflective of the U.S. Midwest, but is, again, very dependent on locations. The default is reflective of the U.S. Midwest. And then the financing parameters that Brentan talked about earlier can be adjusted. And then down here at the bottom is where you can either select calculate for me and use the Scalar default labor model that I previously discussed, or if you select enter manually, you can enter the number of operators, the number of daytime staff, and the number of lab personnel. At this point, once you've filled in as much as you can, you can hit generate my initial report. And I went ahead and so we don't have to wait another 30 seconds for the report to be calculated. I went ahead and ran this before the call. So this is going to be the default Scalar report that you get. The first three things here is, again, how much product is produced on an annual basis, the CapEx for the facility, excluding the contingency and financing costs, and then this direct cost on a kg basis, that's the variable and fixed COGS, so that excludes the capital service costs. Moving down into fully loaded costs, this is where we add on the capital service cost to the direct cost to get a fully loaded cost of production. The net profit is just the product pricing that you provided minus the total cost of production, and then here's the profit margin. On the next section is the sensitivity analysis. This is where we show a tornado diagram. How to read this tornado diagram is we hold all of the process parameters at their inputs, but we vary the process parameter here on the left plus 25% and minus 25%, so that you can see how that parameter impacts the net profit. And then on the next set here, we show the two most sensitive model parameters and how how variations in those model parameters have an impact on the net profit within plus or minus 30% of the CapEx that's calculated. So the middle line is representative of the CapEx that's calculated, and then minus 30% and plus 30%. Here's the CapEx breakdown that I showed earlier. Again, the equipment price is determined based off of that priced equipment list. The building price is based off of estimating the square footage for the facility in dollars per square foot for different process areas. And then the rest of the construction bulks and indirects are factored. And then moving on, here's the COGS breakdown. with these first two sections making up that $14 that we saw up here as the direct cost, and then layering on the capital service cost gives you your fully loaded cost here of $24. And I'll turn it over to Brentan to just step through the bankability analysis portion of the report.
Yeah, so the next section talks about the bankability piece. And so the total capital need here, the 376, that's in comparison to the facility cost of 302 that is part of the CapEx breakdown above. So that includes all the soft costs, which are shown in the sources and uses. We then show the debt that's available for the project based on the calculation. So for this particular input, the debt available maxed out at the 65%. So that shows that it has healthy cash flows to support a fair amount of debt. And finally, the project returns. And so what are the levered IRR for the remainder of cash flows? This is showing 32%, which is significantly above the 18% hurdle that Scalar is requiring for the equity side. And so everything here is showing up nice and green, showing that the project is quite bankable. We also try to show a facility utilization plot. The idea here is to say, your equity investors theoretically can take a 0% return. Your debt investors cannot. If you don't pay your debt, they can foreclose on the facility and take it from you. And so this is trying to get a sense of, in downside situations, what utilization would you need to hit for the facility in order to be able to cover your debt service and avoid your debt lender coming in and actually taking it from you. And so in this situation, it's showing there's actually a fair amount of headroom, only needs to be at 33% utilization. So if the market went different than you were expecting, couldn't sell as much product, your equity investors may not be happy, but you'd still be a going concern. Finally, we provide a very high level calculation that tries to compare on versus off balance sheet. So off balance sheet is the project finance model. On balance sheet would be using corporate equity with dilution. We make some assumptions around what that dilution would look like to calculate what the equity value increase for your current investors looks like for a facility. And so the idea is upfront off balance sheet, there's some savings associated with having third-party capital instead of having to dilute yourself. And so the amount of cash that you have to provide from the corporate level to actually build is $118 million lower in the off-balance sheet scenario because you're using third-party capital. Whereas in the on-balance sheet scenario, you'd have to have $118 million in corporate cash to spend. And it's showing in this particular scenario that the equity value for current investors pre-dilution is 140 million higher in the off-balance case than it would be in the on-balance sheet case, simply because the EBITDA multiplier for the project is diluted by new investors coming in. And so current investors see less of the enterprise value increase from having access to a facility when it's done on balance sheet versus off balance sheet. Finally, we provide a couple of scenarios. So based on the input fermentation sizes that were provided, we run the Scalar model at a couple sizes larger and smaller to give a sense of how the facility cost trends based on total size and what that means for both direct costs as well as total fully loaded costs with financing. So this gives a sense of, as you go from 700,000 liter facilities to 2.5 million liter facilities, what does that mean for your unit economics? Bigger is obviously better from a scale impact, but bigger is harder to finance, bigger check sizes, more commercial demand needs to be shown. So this is trying to give a sense of what that trade-off looks like to help in decision-making. And finally, a list of all the provided inputs so that you can compare and contrast different model runs against each other and know exactly what you provided to Scalar to generate the outputs that you're seeing. So that's the inside scoop on Scalar. We appreciate everybody's time. Any questions that aren't answered today or any deeper insights, feel free to reach us at contact@synonym.bio. I know that looks like a black hole email address, but it is in fact not. It goes to one person and she does answer them. So please follow us on LinkedIn, email us any questions that aren't answered today. But looking forward to jumping into the Q&A here and seeing what other questions we can answer.
Awesome. Thank you so very much, Brentan and Crystal, for this wonderful presentation. It's clear just how valuable this tool will be in aiding our ecosystem and in key decision making as it moves towards greater and greater degrees of scale. So thank you very, very much for sharing what you've built with our community today. I will invite my colleagues, Dr. Adam Lehman and Dr. Lucas Eastham, onto the stage now to help us moderate Q&A, and I will pass it over to Adam and Lucas.
Thank you so much, Crystal and Brentan. Thank you, Amy, for that transition. First of all, wonderful tool. Thank you so much for being here today. And I really appreciate the framing from both the engineering scientific perspective and also the capital financing perspective. And that's why I think we wanted to bring that here today for both the science of community as well as the business of community. We often think of sugar, power, and labor as our top three, but it's important to have that capital side in mind. So I think with that in mind, I think the high level question that George Tong asked in the Q&A is really important. So he asks, if I wanted to make a company that reduces costs for fermentation companies, what do you folks think would be the best driver of cost to tackle and to reduce?
Well, that's a great question. So certainly when we think about aseptic aerobic fermentation, the high cost and high electrical requirements are often in the fermentation area have to do with the high mass and heat transfer requirements within the fermenter, as well as the sterility requirements of the fermenter. So when we design a bioreactor, we think mass transfer, heat transfer, and sterility. So certainly the high cost of the fermenters for aseptic fermentation has to do with the need to steam sterilize those fermenters and having pressure vessels, as well as all of the sterile instrumentation and valving that goes along with that system. So certainly there's areas of innovation that could happen to around the fermenter design to reduce capital costs there. And then also, again, within the mass transfer and heat transfer requirements to help reduce some energy there. Brentan, do you want to take a stab at that, thinking through not just direct CapEx and OpEx, but on the cost of capital as well?
Yeah, I mean, the driving financing costs down is primarily an exercise in getting more stuff out into the world and having more proof points. And so people have more confidence in a sector and therefore are willing to lend it at lower rates because they see it as less risky. That's not a very satisfying answer, but it sort of is an answer on that piece of it. The other area I would point to is standardization. Everybody, if you think of a data center, everyone sort of knows what a data center looks like, and they have racks of servers, and it's all sort of standardized in how it looks. It wasn't always that way, right? In the early 90s, you had a bunch of computers wired together in basements of office buildings, and that was a data center. The standardization of that helped drive down design costs, construction costs, a lot of the soft costs associated with building these things. Similar efforts, which is we spend time on a Synonym, is important to drive down costs for actually building these facilities. Multiples, not just one.
Great, thanks. We'll take the next question here from the Q&A that's been upvoted, and I'll paraphrase a little bit. So Bryce Rogers asked, we assume within the model in Scalar that the greenfield construction facility will be used. Do you have any advice around using the tool and considering a CMO facility, or how this might work for the potential for companies to use this tool and bring that information to a CMO?
Brentan, do you want to maybe take a stab at that one, and I can fill in on the technical side?
Yeah, I mean there's a couple pieces there, right? So it's in our roadmap to try to think about how do we incorporate CMO pricing and those kinds of things for Scalar. It gets more difficult because each CMO is different and the facilities they provide are different. And so from a very basic level, if you had a CMO that had everything you needed, then the capital portion of the model is sort of irrelevant. It's much more the operating cost portion of the model is still very, very relevant. The parameters that you use for that operating cost portion of the model should be based on the CMO capabilities. It gets more complicated when you have CMOs that only have a portion of what you need. Maybe they have the fermentation, but not the DSP or something along those lines. And in that case, the back end of Scalar can definitely calculate the equipment across the entire facility. What's exposed to the user in the output is just the total number. But by getting in contact with us, we'd be able to demystify that a little bit to give a sense of like, well, what is the price of the DSP you'd need to bring to the table, and what would that look like in financing? So it requires a bit more surgery, which we can do manually if you contact us. We're still working on in our roadmap to figure out how we can make that work more automated.
Yeah, I don't have much to add. It's just a matter of taking that that sized and priced equipment list that's developed in the Scalar engine, like Brentan said, and cross-referencing that with what's existing at the CMO to understand the capital requirements that would be required, and that will be different depending on the scale as well as what's available at the existing facility.
Wonderful, thank you both. I think the number of questions on financing is very indicative of everyone's mindset in the chat here. I guess maybe I'll tie two questions together. The first being, do you have a facility life, or I thought it was built into the model? You have a 20% runtime on the debt service, but you have a 30-year, 40-year on the facility life. And then also from David Brandis that Zach has put in, what percentage of the debt service coverage do you recommend producers to have locked in take or pay agreements to pass as bankable?
Yeah, so good questions. We assume a 20-year asset life. So when we're doing equity return calculations, that's on a 20-year asset life. We could make it longer. We could make that an input to the model. Although once you get past 20 years, because it gets depreciated so heavily at 18%, it kind of doesn't matter. But we do assume a 20-year asset life. In terms of coverage ratios, I think the best data points would be some things like in the biofuel space, where they have long-term take or pay contracts, 10-year type offtakes at either fixed or index price that can be hedged. Those are like very, very bankable offtakes with, tier one IG counterparties. For folks that are perceived as new technology risk, they still need a coverage ratio comfortably at 1.7. Maybe you can squeeze to 1.6. If you have technology that's considered well developed, so like folks in the anaerobic digestion space making biogas that have good offtakes for biogas, they can get down to like 1.5, 1.4 in the coverage ratio. To give you a sense of like, if you are a commercial real estate developer building like a shopping center and you have your anchor tenant from like a public company that's IG with a 10-year lease, you could get your coverages down to like 1.05, maybe 1.1. So it really, hopefully that gives you a couple data points of sort of as you move down the risk profile, you can approach almost a 1 coverage where things are ironclad and there's sort of like no chance of default.
Great, thanks for those insights. And I think this really does speak to the power of the tool to think about the financing costs that are really wrapped up in the biology that everybody typically thinks about in the bio process. A question here that's a little bit different, and it was touched on, is the question is, do we calculate greenhouse gases for other inputs and costs? So you spoke a little bit to the potential to have Scalar be used as a life cycle assessment tool in some way. If you want to elaborate a little more on that, I think this would be a great time to do that.
Yeah, I mean, it's something we're exploring at the moment. It's hard to do a full LCA, but we're trying to figure out if you could do sort of a abbreviated version that gets you to sort of the loading dock on the output side of the facility. If you know where the facility is located, you know how much electricity you use, you know what sugar you use, you know which power or natural gas you use, and you can determine the embedded greenhouse gas in each one of those inputs. You can come up with a basic assumption of sort of the embedded carbon in the product itself. That's easier said than done. Trying to find those metrics and how they work is something we're in the process of exploring. We also know there's great work being done at GFI right now on LCAs, which we're also exploring if there's ways to utilize some of that information in Scalar to drive that forward as well. But that is definitely something top of mind for us that we hope to integrate into the tool in the near future to at least give a sense of how different parameters impact the embedded carbon in the product itself.
Yeah, 100% on that. And data. An LCA is quite useless without data. So we encourage anyone here that wants to help collaborate on the LCA project with Foodsteps and GFI. Please reach out. I don't have the contact right on hand, but we can post that again about who to reach out to regarding our food steps collaboration. I guess related to LCAs and heat, are there any like heat efficiencies metrics that you can build into the model, and or what is the base for the mass balance there? It's just single in and out, or do you have any heat recovery assumptions?
Yeah, so we do have heat recovery assumptions. So in the base model, we're using continuous sterilizers for media and feedstock sterilization. Those continuous sterilizers will incorporate an economizer on there. So instead of just doing sterilization in the tank, which requires more steam to do so, there's an economizer that can recover 75 to 80% of the heat that's put into the stream for that continuous sterilization. So that's one area where the model already reduces the amount of steam usage. Another, I mentioned it during the presentation, is utilizing a free cooling. So the model assumes that we have separate fermentation chillers from the downstream process chillers. That way the fermentation chillers can operate at a higher supply temperature. And in the winter months, when the cooling tower water is cool enough to support most fermentation temperatures, we utilize free cooling. And so the chiller systems are not operating during that time. So the higher the fermentation temperature, the longer percentage of the year you can have full cooling and not have to operate the chiller compressors for that. So those are already taken into account. And then another thing in terms of natural gas usage is the biomass valorization for precision fermentation processes. A lot of times the cell mass that's produced is significantly more than the product that's being produced, and so drying of that cell mass can be a huge heat load. And so we have questions in Scalar to also try to identify that.
Fantastic. That's really well thought out. It's a really neat part of it. Unfortunately, we're at the end of our time. I'm again very grateful to everyone from Synonym for being part of our seminar series. And I would encourage everybody who has an unanswered question to follow up at contact@synonym.bio with those questions. It sounds like there's some questions about future capabilities and integrating different parts of the bioeconomy and different units and things like that. But I'd like to thank all of you for your attention and your wonderful questions. And yeah, we'll conclude here, and I wish everybody a great day. And we'll see you for our next seminar on October 19th. And hopefully we'll see everybody at GFC instead for September. Great. Thanks, y'all.
Yes, thank you.
Thank you.
Thanks, everyone.